Hello, my name is Mike Krogert. I am the Senior Industry Product Manager for Flowmaster, with specific responsibility for the power and energy markets. Today, I will be discussing Flowmaster's power generation product offering. The topics for today are a brief description of Flowmaster's power generation product. Next, I will look at the specific needs of the power generation market, the unique challenges of two-phase flow simulation, and finally, Flowmaster's implementation of two-phase flow. For a brief description of what Flowmaster version 7.9.0 power generation is, it is the complete Rankine cycle modeling, enabling the user to simulate and optimize any portion or the entire power generation steam cycle. Also evaluate system reconfiguration and fail scenarios for fossil fuel, solar, and alternative power plants. What are the concerns in a traditional fossil fuel power plant? Operators are looking to optimize the efficiency and minimize the downtime of their plants. As a designer, it is critical to understand how the system reacts to every possible control and fail scenario. An additional concern is accuracy and consistency of the simulation tool so the regulatory commissions have confidence in the analyses that have been run. Solar power plants have inherent unknown due to the uncontrollable power source. The heat that can be generated by the sun is dependent on location, season, and weather. All of this requires constant control of the heating fluid to maintain a consistent flow of heat to the steam generator. Additionally, solar power plants are typically built in hot, arid environments to optimize the amount of usable sun energy. The dry environment means that there is a higher loss of water due to evaporation. Since the water is a scarce resource, its usage must also be closely managed. They are also looking at alternative fuel sources such as biofuels and renewables. Additionally, they are investigating supplementary power sources such as gas turbines to handle peak loads and to handle the primary load when the main power source is taken offline for maintenance. Fuel quality, atmospheric conditions, and demand all influence the operation of a power plant. Operators are looking for tools that will help them create an optimized control strategy to operate a power plant as efficiently and cost-effectively as possible. One of the key requirements of two-phase flow modeling is to properly simulate the complete Rankine cycle. There are 4 processes in the Rankine cycle. These states are identified by number in the diagram on the right. The process from 1 to 2, the working fluid is pumped from a low to a high pressure. As the fluid is in liquid state at this stage, the pump requires little input in energy. The process from point 2 to point 3, the high pressure liquid enters a boiler where it is heated at a constant pressure by an external heat source to become a dry saturated vapor. The process 3 to 4, the dry saturated vapor expands through a turbine generating power. This decreases the temperature and pressure of the vapor and some condensation may occur. Finally, step 4 to step 1. The wet vapor then enters a condenser where it is condensed at a constant pressure and temperature to become a saturated liquid. The pressure and temperature of the condenser is fixed by the temperature of the cooling coils as the fluid is undergoing a phase change. This is the theoretical Rankine cycle, but there are several variations of this that occur in the real world. For example, if you superheat the steam. Rankine cycle with superheat is often called the real or non-ideal Rankine cycle. This is a typical cycle for a single turbine power generation system. The steam is superheated before it enters the turbine to prevent water from forming and damaging the turbine blades. Another variation of the Rankine cycle is Rankine cycle with reheat. This is a typical configuration for a two-turbine system where there are high and low pressure turbines in series. The steam is reheated after it exits from a high pressure turbine and before it enters the low pressure turbine. Finally, there is a regenerative Rankine cycle. In a regenerative system, steam is bled off the turbine and is mixed with the water after the condenser and before it enters into the boiler. Alternatively, the bleed steam is routed through a feed water heater. In either case, this effectively preheats the water before it enters the boiler. This is a typical configure of actual power plants. Flowmaster, as with most flow solvers, uses fluid properties data and a defined set of correlations to predict the pressures, temperatures, and flow rates in the system. When phase change occurs, there is a near instantaneous change in the fluid properties, as can be seen in the plot of the enthalpy of water. Just a slight change in temperature or pressure in the system can have a dramatic effect on the fluid properties. This can cause inaccuracies and instability in the solver if not handled properly. This can be mitigated through very well-defined fluid property surfaces that have enough data points to allow for smooth, continuous surface fits. While accurate fluid properties data will reduce the issues, the solver and related components must be robust enough to recognize these near instantaneous changes and handle them appropriately. There are three different stages of boiling that occur depending on what the temperature differences is between the liquid and the heating surface. Those are nucleate, transition, and film boiling. Nucleate boiling is the first stage where small bubbles of vapor form on the heating surface and then break free. This continues as the temperature difference increases until the critical heat flux is reached. At this point, it is in the transition boiling zone, which is not desirable. In this area, the heat flux actually decreases as temperature increases until film boiling begins to occur. This is when the heat flux is at its minimum and then increases as the temperature difference increases. For the majority of the systems that will be modeled in Flowmaster, nucleate boiling will be the desired operating range, since this is the most efficient heat transfer with the limited amount of energy added. It will be important for Flowmaster to recognize when the transitional regime is reached, though, since this will have a significant impact on heat transfer, and it can also cause large vapor cavities to form that can cause blockages. Additionally, if these cavities were to burst or collapse, they can cause large pressure waves in the system, resulting in steam hammer. Condensation is the cooling of the vapor until the phase change back to liquid occurs. Condensation can occur in two manners, controlled or uncontrolled. Controlled condensation is when components such as heat exchangers are added to the system with a distinct purpose of converting the vapor back into liquid. This is done for the purpose of reuse in closed cycle and also to stop uncontrolled condensation. Uncontrolled condensation occurs in systems when the temperature of the vapor is reduced because of heat loss to the surroundings, until small liquid droplets begin to form on the surfaces. As more and more droplets form, they merge and begin to flow along the bottom of the pipe. This buildup of liquid begins to affect the flow of the vapor and can have damaging effects on the systems. In cases of vertical or inclined piping, the liquid will flow in the reverse direction of the vapor or at a faster rate if they are moving in the same direction. Again, this slip flow also has an effect on the flow rates and pressure drops in the systems. Mitigation components such as steam traps will also need to be provided to allow the draining of the condensate out of the system. Natural circulation is a thermal fluid property phenomenon that is taken advantage of within the power generation industry. This is the ability of a fluid within a piping system to circulate or flow continuously without the means of a pump. The combination of changes in heat energy and gravity work together to cause the circulation. This is a typical configuration that is used in water tube boilers and heat recovery steam generators. The ability to simulate this phenomenon accurately is key for the market acceptance of the product. Flashing or flash evaporation is a phenomenon that occurs when high pressure saturated liquid has a rapid pressure drop. When this occurs, part of the liquid is converted to vapor in an isenthalpic process, and a resulting mixture of vapor and liquid occurs. This is utilized in many systems to efficiently create steam in high-pressure systems, as in geothermal applications. Superheated steam is principally used in power generation plants as the driving force for turbines. This is done for two reasons. First, as per the Rankine cycle, superheated steam is thermally more efficient than saturated steam for powering turbines. Secondly, wet steam can cause formation of water droplets on the turbine blades. These droplets cause erosion of the blades, which increase friction and reduce the life of the turbine. Other benefits include higher pipeline velocity, which allows for smaller distribution piping systems, and the fact that there is no condensation in the piping systems, which eliminates the need and cost of most mitigation devices. The downside of superheated steam is that the usable energy in the superheat is quite small compared to the enthalpy of evaporation. The diagram on the right shows the typical enthalpy split of superheated steam. Additionally, the heat transfer coefficient of superheated steam is much lower than that of saturated steam and can be variable and difficult to predict. This causes an issue with the ability to properly size components for particular systems. If superheated steam is used as a heating source, it is typically also required to have a larger and more expensive heat exchanger than a wet steam system. These disadvantages mean that superheated steam is generally undesirable for thermal process applications. However, sites exist where superheated steam is raised for power generation, and it makes economic sense to desuperheat some of the steam from some point in the power generation cycle and then use it for process applications. In plants that have superheated steam available for process use, it makes sense to distribute the superheated steam to remote points in the plant, as it will ensure the steam remains dry. This becomes significant if there are long lengths of pipe separating the point of generation and the point of use. Once the superheated steam reaches the point where it will be used, the superheat must be reduced. This involves injecting water into the superheated flows. The water is vaporized and the steam downstream is cooled to the saturation temperature and has the additional mass of the water added into the steam. This change in enthalpy and mass must accurately be accounted for as part of any two-phase solution. One of the unique features of two-phase flow is that depending on the orientation, temperature, and pressures, the flow patterns are very different. Each of these flow patterns have an impact on the pressure drop and heat transfer in pipes. It is critical that Flowmaster recognizes and models these different flow patterns accurately. The flow conditions in a horizontal pipe are very different than those in a vertical pipe. One of the most difficult aspects of modeling two-phase flow is steam hammer effects. This is similar to water hammer, but the consequences of steam hammer can be much more severe than in liquid systems. Because of the level of stored energy both in the temperature and pressure makes systems failures potentially catastrophic. In liquid systems, pressure waves are typically generated through some sort of dynamic action in the system, such as a rapid valve closure. While this can also occur in steam systems, the less predictable and potentially more dangerous cause is uncontrolled condensation. The diagram here shows how this can occur in a system. Steam residing over a subcooled condensate loses heat to the condensate in the surrounding pipe, which causes some of the steam to condense. Continual loss of steam induces fresh steam to flow into the pipe to replace it. The steam flow over the condensate will tend to draw up a wave in the condensate via the Bernoulli effect. If the rate of heat transfer is rapid enough for a given condensate level, the induced steam velocity will draw up a wave high enough to seal the pipe. The creation of the seal immediately isolates the downstream steam pocket from the upstream supply, creating a steam pocket. Ongoing condensation in the isolated steam pocket drops the pressure, causing a slug to accelerate into the void, collapsing the steam pocket. This results in a reflective wave that can cause severe damage to the piping system. We will now discuss the implementation in Flowmaster of its two-phase flow simulation capabilities. The integration of two-phase flow modeling capabilities within Flowmaster required the development of an entirely new energy solver that was based on the propagation of enthalpy rather than temperature, as was done in the traditional Flowmaster solver. This new energy solver and required framework was developed and implemented at version 7.8. From this baseline, the two-phase flow simulation has been developed. Additionally, more accurate fluid property data was required for two-phase flow simulation. With this in mind, we've integrated NIST RefProp 9.0 fluid properties database into Flowmaster. An additional challenge of the NIST database is the large number of data points for the fluid properties. This can have a significant impact on the performance of the software due to the high memory usage. To minimize this, Flowmaster has implemented intelligent data point generation, which creates fluid property surfaces that have a variable point density. This utility places fewer points where there is little change in the surface and more points where the changes are more significant. This provides fluid property accuracy across a range of temperatures and pressures while minimizing the database size and the analysis time required. The new two-phase specific pipe has been designed to be versatile and flexible. A single component can model pure liquid flow, two-phase flow, and pure vapor flow depending on the conditions specified. The user does not have to know where the phase begins to change or the type of flow regime which is occurring within the particular pipe. The software will evaluate the conditions and determine the correct modeling correlations to apply. It can determine the heating or cooling conditions applied to the pipe or segment of pipe and apply single-phase heating or cooling, boiling, evaporation, or condensation effects as is appropriate. This gives the user the flexibility to set up a model without being restricted by having to predefine the flow conditions at any one point in their model. This will allow them to run unrestricted what-if scenarios and failure mode analysis anywhere in a simple or complex Rankine cycle, such as a regenerative Rankine cycle that is typical in a powered plant steam cycle. For two-phase flow, there are multiple flow regimes which are also dependent on the orientation of the pipe. Additionally, each of these flow regimes have a different effect on frictional losses and heat transfer within the pipe. Flowmaster provides two different pressure drop models. First, the homogeneous approach. It assumes a pseudo-fluid condition where traditional single-phase fluid design equations are applied. To do this, fluid properties of the liquid and vapor phases are averaged. The critical assumption of a homogeneous flow model is that both phases have the same velocity and the mixture is homogeneous. The second approach is the separated flow approach. The separated mixture approach assumes the liquid and vapor phases are separate into two streams, each flowing in its own pipe, therefore allowing single-phase assumptions to be applied. The area of these pipes is proportional to the void fraction. This approach has the advantages that it does not have the assumption that the vapor and liquid portions have the same velocities. Flowmaster gives the user the choice of 4 different frictional pressure drop models to allow them to best fit their modeling needs. These are the Friedel correlation, Lockhart-Martinelli, Chisholm correlation, and the Mueller-Steinhagen and Heck correlation. When considering two-phase flow, heat transfer and flow regime modeling is the key to having a viable solution. Boiling, condensation, and flow regime identification are all dependent on temperature and the heat added or extracted from the fluid. This is further complicated by gravitational effects on the fluid and flow regimes. These complications are due to the fact that inertia, viscosity, and buoyancy effects can be attributed to both liquid phase and to the vapor phase, and also due to the impact of surface tension effects. Therefore, it is critical to understand not only energy inputs but also the orientation of the pipe when modeling the heat transfer effects of the two-phase pipe. Flowmaster has implemented correlations that identify the orientation, flow regime, and heat transfer states and applies the appropriate heat transfer coefficient. It can also identify the location in the pipe where critical heat flux occurs. This approach provides the user with the flexibility of choosing the most appropriate pressure drop correlations and accurate heat transfer calculations for any pipe orientation. We will now discuss some of the power generation specific components that have been developed for Flowmaster. The first component that we will discuss is the water tube boiler. This is a four-arm component that models the heat transfer between the flue gases and the water steam mixture. This component integrates the two-phase pipe model to model the water wall of the water tube boiler. This is the key component as shown here on the right. It loops between the steam drum component, enabling natural circulation through the furnace. The next component is the superheater and reheater component. This is a four-arm cross-flow heat exchanger component which adds superheat to the steam before it enters the turbine. It connects downstream from the drum component and also connects to the downstream from the furnace on the flue gas side. The heat transfer from the flue gases to the working fluid uses convection as well as radiation. This diagram shows the complete liquid system and flue gas system of the furnace. If we look beginning at the drum, we can see the liquid circuit where the water flows downward from the drum through the downcomer pipe into the liquid side of the water tube boiler component and then back into the drum. This is the natural circulation section of the model. If we then look from the pressure source through the water tube boiler up through the superheater and through the individual reheaters, we see the flue gas flow for the furnace. Flowmaster has also implemented a steam turbine component. This component is flexible enough to model either the entire turbine as a single component or each stage individually. It is a truly transient component with internal stage pressures varies according to the accumulated mass. Additional to the new steam turbine, we have implemented a steam turbine shaft component. This component is used to accumulate the power generated from one or more of the stages of the turbine. Flowmaster has also implemented a power generation specific condenser component. Again, this is a four-arm component with two distinct circuits. The tube side, which is arms 1 to 2, which models the cooling water circuit, and arms 3 to 4, which is the steam condensate circuit. This component also has a virtual fifth arm that allows the internal pressure of the condenser to be set as a vacuum. This also will take into account any uncondensed steam vapor that is ejected from the system through this fifth arm. It properly tracks both the mass and energy loss through this arm. Flowmaster provides three different types of cooling towers components as well. A wet cooling tower, which is based on the Merkel approach, which is the widely accepted approach within the power generation industry. Dry cooling tower, which is basically a heat exchanger with a fan. This is the type of cooling tower that is used in building applications typically. And then the hybrid cooling tower, which is a modification of the Merkel approach as well. Both the wet and the hybrid cooling towers also model evaporative cooling. This allows the user to take into account environmental conditions including temperature and humidity. This diagram here shows you the complete cooling water circuit in a simplified power plant model. On the upper left hand side we have the condenser, which the cooling water exits to the cooling tower, which has a airflow stream through it, which cools the water. The water is then pumped back to a reservoir, and the cycle repeats by the water being pumped to the condenser. Flowmaster also provides three different types of steam traps: mechanical, thermodynamic, and thermostatic. We provide two different types of mechanical steam traps, a ball float and an inverted bucket steam trap. Basically, these are all check valves used to remove condensate from the piping system without allowing steam to escape. There are three-arm components where the steam and condensate mixture enter, and the condensate is trapped in a drip leg and the steam continues downstream. When conditions are met, such as temperature, liquid level, or temperature difference, the trap opens and releases condensate. Finally, in summary, this diagram simply shows the different types of results that can be determined at different parts of the power plant system. The power plant system consists of three separate fluid circuits. You have the steam circuit, the cooling water circuit, and the flue gas circuit. These all can be modeled simultaneously within Flowmaster. And finally, this final diagram is just an example of a fossil fuel power plant and how it can be modeled in Flowmaster. Thank you, and I hope you found the presentation informative.